speaker is Dariusz Ucinski, and he's going to talk to us on the construction of constrained optimum designs.
Thank you very much. I must admit that it's hard to imagine a better introduction to the topic of my contribution than Ben's nice talk about the multiplicative algorithm. This is because what I'm going to present you is closely related to that talk. Namely, I'm going to present you that when combined with a slightly different algorithm, which has been used so far in completely different engineering problems for traffic assignment and network flow optimization, when combined that algorithm called simplicial decomposition with the multiplicative algorithm, it is possible to solve problems in the same setting, but including additionally linear constraints on the weights. What is more, the main feature of the multiplicative algorithm is retained, namely the extreme simplicity of the whole stuff. To be more precise, let's recall that optimum designs are identified with probability distributions on the design space. There are two classes of algorithms, roughly speaking. In the first class, we use sequential algorithms which, during the work, sequentially change support points of those distributions, and simultaneously they tune the associated weights. And the work of those algorithms, called generally the Wien-Fedorov scheme, the work of those algorithms is much like that of feasible directions algorithms in nonlinear programming. We can look at the same problem from a different perspective, and we can cover the design space with a network of points. The number of such points is finite. Those points which are assumed to be support points those points are fixed, and we focus our attention on tuning the weights. This simplifies many things, and we have a nice optimization problem. Ben has just showed you that we can use here the multiplicative algorithm, which is very easy to implement. Both classes of those algorithms have been refined over the past decades, so they've become classical, but in practice, often we have a situation when various inequality constraints resulting from cost limitations, restrictions on stemming from some robustness requirements or restrictions on the experimental space must be included in the formulation. Although much theoretical work has been done in this respect, starting from the seminal work by Cook and Fedorov, the number of publications on the corresponding algorithmic aspects is by far insufficient. So what I'm going to show you is to present an attempt to combine the multiplicative scheme with inequality constraints on the weights. So to start with, let's consider a parametric model. This is a quite classical setting. We assume that we can observe a vector of responses at fixed values of explanatory variables. The second index, j, is necessary here because we allow for replications. And the number of replications for each setting of explanatory variables will be denoted by Ri. The total number of experimental runs will be denoted by capital N. Eta is known regression function, and we strive to recover the value of an estimate of a vector of constant but unknown parameters, denoted in what follows by theta. As for random errors, the assumptions are also classical. We assume that they have zero means. They are uncorrelated for different settings, but we allow for correlations among responses for particular setting. The curly inequality sign for matrices denotes that a matrix is positive definite here. In a linear setting, this model is simplified. Namely, the regression function eta becomes the product of some known matrix by the vector of unknown parameters. In this simple setting, the best linear unbiased estimator of theta takes the well-known form, and in this expression, the matrix M, called the Fisher information matrix, is crucial. Here, it is just the sum of n matrices, capital Mi. You can see here the expression defining those matrices. Those matrices are weighted by the numbers of replications at the corresponding design points. In this setting, the covariance matrix for the estimator is just the inverse of the information matrix. We assume that the settings xi, this may correspond to settings of time, temperature, drug doses, etc. Those settings are fixed, and we assume that we have, however, full control over the corresponding numbers of replications Ri. We wish to choose them in an optimum way to enhance the process of estimating theta. In the classical literature, the problem is formulating just as looking for an optimum design, which is represented usually in tabular form. But here we can simplify things, because the support points are fixed, and we are looking just for the weights pi, which are defined as the ratios of the number of replications at the corresponding points by the total number of experimental runs. The property recalled by Ben can be shown here, that those weights have the property of classical discrete probability distribution. As for the notation, the bold 1 will denote the vector of unit values. It is much more customary, much more convenient to operate not just on the information matrix, but on its normalized version, which is just the information matrix divided by the number of experimental runs. With this convention, the normalized information matrix is just the convex combination of elementary information matrices, capital Mi. And in order to make the elements of the covariance matrix for the estimators as small as possible, we can formulate the problem, we can reduce it in optimization terms as that of maximizing the determinant of this information matrix. For simplicity of notation, the tilde of capital M will be dropped in what follows. The first problem we encounter when you try to solve this problem numerically is that it has purely combinational nature, and thus it suffers from the curse of dimensionality and many related problems. So in order to overcome this difficulty, we usually relax the formulation by assuming that the weights can be all numbers from the interval 0, 1, which sum up to unity and not necessarily integer multiples of the reciprocal of the number of the total number of experimental runs. So this is classical, and this makes it possible to invent such simple and effective algorithms as the multiplicative algorithm recalled in the previous talk. But another difficulty is that as you know, that optimum designs concentrate at a relatively small number of support points. This number is often close to the number of estimated parameters, and from a practical point of view, this may be inconvenient. And many statisticians prefer to spread measurements over the design region anyway. So how to cope with this problem? We can do it as follows. We can impose some additional constraints, and in what follows, I'm going to focus your attention on the simplest constraint as can be imagined. Namely, we bound the weights from above. And we assume that the vector of upper bounds is fixed. As for the notation, the curly inequality here, because we have here vectors, should be understood component-wise. This notation is currently used in convex optimization. So our ultimate formulation is as follows. Given a vector of upper bounds on the weights, we wish to find a vector of the weights p, which maximizes the determinant or the log determinant, which is the same of the information matrix, subject to the following constraints. So the unusual element here is the presence of this inequality constraint. From the point of view of convex optimization, this is a very nice problem because we have a concave function which should be maximized, subject to a very nice constraint set. Namely, you can note here that the constraint set is just the intersection of a box in the space of weights and a hyperplane. In other words, at the intersection of a box and the canonical simplex, the result is the same. Another nice thing is that the components of the gradient can be computed here with relative ease. Well, the formulae are well known. And then it turns out that when we have the constraint set, which is the intersection of a box and a hyperplane, a very efficient algorithm exists for projecting onto this set. So this algorithm can be potentially used to implement the conditional gradient method or a gradient projection method here. But if the number of support points is large, the results can be quite unsatisfactory. Well, another issue is that we have to implement this anyway, so this may take some additional time. So in what follows, I'd like to show you that it's possible to solve this problem with relative ease, almost in the same way as the classical multiplicative algorithm works. Here you can see the counterpart of the equivalence theorem here in this setting, namely a vector P star constitutes a global maximum to the de-optimality criterion over the constraint set I've just mentioned, if and only if there exists a number denoted here by lambda, such that if you have weights which are between 0 and the corresponding upper bounds, those weights, for those weights, the corresponding gradient of the de-optimality criterion are the same. They are equal to this number lambda. As for the weights which attain their maximum values, the corresponding gradient components must be no less than lambda. And as for the weights which are 0, the corresponding gradient components mustn't be less than lambda. So this is a quite nice result, and it can be easily checked in practice. But this is only a condition to check if we have or not an optimum solution. The problem is how to achieve this optimum solution numerically. And it turns out that the algorithm called simplicial decomposition can be used here. It has origins in the 1970s, and it has been used in network flow optimization problems or traffic assignment, and it is aimed at solving large scale problems. And basically it works by alternately solving two simpler problems. So the name's decomposition results from this splitting. First, a linear programming problem is solved. In this linear programming problem, we operate on the same constraint set, but the form of the function which is maximized is simpler because we have just a linear function. This problem is called the column generation problem. The second problem is the so-called restricted master problem. In this problem, conversely, we maximize the original nonlinear function, the de-optimality criterion in our case, but on a simpler constraint set. This set is just the convex hull of previously fine extreme points. Extreme points are determined by the work of the first part of the column generation, of the algorithm solving the column generation problem. And it turns out that one of the main features of this scheme is that the consecutive iterates converge to the solution such that the objective function tends monotonically to the solution of the original problem. In order to show you how it works in practice, let's consider a simple example. Here we have two weights, P1 and P2. We have the objective function. You can see here contour lines. And we wish to find the maximum of this function over this constraint set represented here by white square. Well, we start by choosing the initial point. Based on optimality conditions, we see that this is not the optimum solution yet, so we continue. We pass to the column generation problem, in which we find the point which is furthest along the gradient direction from the initial solution. This furthest point is here. So this is the first extreme point which is generated. Then we pass to the restricted master problem, in which we maximize the original function, which is just the de-optimality criterion, let's say, over the convex hull of both the points. In this case, this is just the line joining the 2 points. And it is easy to see that the maximum value is attained at this point. Then we pass to checking the optimality conditions. It turns out that this is not end yet. So we pass to the column generation problem. We solve a linear programming problem, and it turns out that the point lying furthest in the direction of the gradient is here. And now we have already 3 points. We take the constraint set, which is now the convex hull of those points, and we maximize the original function on this convex hull. And the best point is here. Now, if we check the optimality conditions, it turns out that this value can be improved, so we terminate. So the idea is quite simple. It is easy to write it down in the form of the corresponding algorithm. So we initialize the weights. We check the termination conditions. We solve the column generation problem, and we solve the restricted master problem. If we don't have an optimum solution, we come back to step 1. As for the column generation problem, I've just mentioned that it is a linear programming problem. Due to the simplicity of the constraint here, we have only bounds from above on the weights. It is possible to show that, well, here you can see an algorithm, but speaking in plain English, we can say that it is sufficient to take consecutive largest components of the gradient vector, set the corresponding weights at the maximum values, and we continue while summing up the corresponding bounds. If then this sum exceeds 1, we stop, we correct the last weight such that the sum is now 1, and then we set the remaining weights as 0. So you don't need any simplex method, any interior point method. The solution is here very simple, and the cost of the solution is like the cost of sorting a vector. As for the restricted master problem, we should maximize the original function on the convex hull of previously obtained extreme points. Well, after some simple algebra, it turns out that this problem amounts to the following form. So we maximize the determinant of a matrix. This matrix is a sum of some simpler matrices multiplied by weights. The sum of those weights is 1, and the weights should be non-negative. Well, this is just the same problem which can be solved by the multiplicative algorithm. So we can solve it easily with no problem. Well, this is the corresponding optimality condition. Well, this is well known. Well, I skip it. As for the example, this, by chance, this is almost the same example as given by Ben. It concerns a batch reactor. We have initially we have only component A, and then in the consecutive reaction, A becomes B, and then B becomes C. The process is governed by 3 equations. We have 4 coefficients here marked in green, and they denote rates and orders of the reaction, and they become our parameters to be identified. Well, there are some assumed, of course, here we have a nonlinear problem, so we obtain only locally the optimum designs. We have 100 potential support points, which are evenly distributed over the interval from 0 to 20. And as for the results, at first, we assume that the weights shouldn't exceed 0.001 35. Well, and you can see the solution here. It turns out that in this case, if I come further, in this case, you can observe the components of the gradient and the weights. The highest weights doesn't exceed 0.31, so this amounts to the purely d-optimum design. And the support points, there are few support points, and they concentrate in the middle of the steep slope of component B and at the extremities of the gentler slope for the same component. If we impose slightly different constraints, bounds are lower, 0.15, you see that the observations become to spread. If we continue, we impose even lower weights, you see the following situation. So you see clusters of points. As for the corresponding variance function of, in other terms, the components of the gradient function, for the first case, this is a purely d-optimum design. The situation is classical. The maximum of this function is attained at the number of parameters. There are 4 parameters here. If the constraints become being active, the situation slightly differs. This dashed line corresponds to the coefficient lambda mentioned in the optimality condition. And for the weights which attain the scale on the right-hand side represents the values of the weights. If there are weights which are which attain the upper bound, 0.15, the values of the variance function exceed this value. And as for zero weights, the values are lower. And as for the weights which are between, the corresponding values of the variance function are equal to lambda. Let's note that this lambda is lower than 4. Otherwise, we could have a purely d-optimum design. Well, these are figures corresponding to reflecting the evolution of the d-optimality criterion. The values of this criterion monotonically converge to the optimum value. Well, there are many refinements which can be mentioned here, and many improvements, but it turns in practice that anyway, this algorithm in its simplest elementary form works perfectly well. We worked on some extensions, so this algorithm was also used to select best measurements sites in sensor networks, and it is possible to extend it to other linear constraints. Of course, the linear programming problem must be then solved using slightly sophisticated techniques, but it is nevertheless possible. It is even possible to extend it to other criteria. Of course, there are some difficulties when implementing the restricted master, the method for solving the restricted master problem, but it is still possible. There are not even possibilities to find parallel versions based on parallel variable distributions and so on. Now we're currently working on extensions toward fully continuous designs, including the selection of support points too. Thank you very much for your attention.
Questions?
At the nonlinear problem stage, which form of the algorithm were you using? Just multiplying by derivatives?
In the case when we don't have a d-optimum criterion, but other criteria, I mean, gradient projection or constraint gradient So this is not a version of the multiplicative algorithm, but I agree that it can be tested. And fit
I
in
think
this.
one other comment, I think your general method is a bit like, I think, an idea that was used in early optimal design, where you work out the optimal design for a current set of support points, and then check the equivalence theorem over the whole design region. And if it's not satisfied, bring in the point with the maximum variance, and augment the design set of support points. So I think you're doing something very similar to that.
It's very similar, yes. Yes. So,
I was going to make exactly the same point, but I didn't hear what you said, Ben, so I might
Yeah,
be
and-
repeating it. So you put mass where it's above, where the influence function is above that, and withdraw mass where it's below, so some kind of exchange algorithm would be, that type would be a competitor. Like a competitor to your algorithm.
well, but as for exchange algorithms, here we can guarantee the convergence to the optimum. It can be proved.
But it doesn't need to be an exchange. It may be that you started out.
I think you're exchanging mass rather than points. I mean, that would be a little bit. Just an idea.
But nevertheless, even in this simple form, it works when implemented in MATLAB, for example, which is not very performant. For the 1,000 of points, you can obtain solutions within several seconds, so it's not a problem.
Okay, I think we've run out of time, so let's thank Dariusz again.